Students, I am Muskan from BSc Chemistry Honors final year. Today I will discuss topics of quantum mechanics. Firstly, we will introduce you what is classical mechanics and failure of classical mechanics. Classical mechanics. Towards the end of the 19th century, physicists were greatly satisfied that they were able to explain most of the phenomena on the basis of Newton's law of motion and Maxwell's electromagnetic wave theory, according to which energy is emitted and absorbed continuously. The former were used to explain the phenomena related to motion, that is, trajectories of planets, falling stones, etc., and the latter to explain the phenomena related to energy transfer. The branch of science based on the Newton law of motion and Maxwell electromagnetic wave theory to explain phenomena related to motion and energy is known as classical mechanics and Newtonian mechanics. What are the failure of classical mechanics? Classical mechanics was able to explain phenomena related to large size objects, that is macroscopic particles. However, it fails when applied to small particles such as electron, atom, molecule, etc. Microscopic particles. For example, according to classical mechanics, it should be possible to determine simultaneously the position and velocity of a moving particle, but this is contradicted by the Heisenberg uncertainty principle. Similarly, classical mechanics assumes that the energy is emitted and absorbed continuously, whereas Planck's quantum theory postulates that energy is emitted or absorbed not continuously but discontinuously in the form of packets of energy called quanta. Further, the concept of quantum numbers was introduced to explain the atomic spectra, a, a few phenomena for which the classical mechanics failed to give a satisfactory explanation are black body radiation, photoelectric effect, heat capacity of solids, atomic and molecular spectra. In the next section, we will discuss how classical mechanics failed to explain the above phenomena and quantum mechanics give satisfactory explanation. Black body and black body radiation. When radiant energy falls on the surface of any body, a part of it is reflected and a part is absorbed, and the rest is transmitted. The whole of the energy is not absorbed because generally the surface of the ordinary body are not perfect absorbers of radiation. However, if the radiant energy is allowed to fall on the blackened material surface or carbon black, it is found that the energy is almost completely absorbed. A body which completely absorbs the radiant energy falling on it is called perfectly black body. The absorption is found to be more perfect if we take a hollow sphere, blackened on the inside and having a small hole for the entry of the radiation. This is because any radiation that enters through the hole is reflected over and again by the wall of the sphere till the finally it is completely absorbed. The most commonly used black body is the one designed by Ferri and is shown in figure 1.1. Black body due to Ferri is shown in figure 1.1. It is a hollow double-barred metallic sphere having a conical projection P. Opposite to the hole, H is coated on the inside with the lamp blank. The projection helps to avoid any direct reflection, as otherwise the body will not act as a black body. Further, a black body is not only a perfect absorber of the radiant energy but is also a perfect radiator. In fact, of all the bodies, the black body radiates the maximum amount of energy for the given temperature. The radiation thus emitted are called black body radiation. Now, what is photoelectric effect? When a beam of light with frequency equal to or greater than a particular value called threshold frequency is allowed to strike the surface of a metal. Electrons are ejected instantaneously from the surface of the metal. This effect is called photoelectric effect. Some important observations about the photoelectric effect are as follow. First is the electrons are ejected only if the frequency of the incident light is equal to or greater than a minimum value called threshold frequency. Second is the electrons are ejected instantaneously. That is, there is no time interval between hitting of the metal surface by the light and the emission of the electrons. The kinetic energy of the emitted electron depends upon the frequency of the incident light. For the photoelectric effect which occur, you will see in the figure 1.5. Fourth is the number of electrons emitted is proportional to the intensity of the incident light. Means higher the intensity of the incident light, more will be the number of electrons ejected. And speed is dependent upon the frequency. According to the classical theory, the energy of the light depends upon its intensity. Thus, if the surface of a metal is exposed continuously to light of any frequency, the electron should keep on gaining energy, and ultimately the energy should become so high that the electron should leave the metal atom. But actually, this does not happen. However, Einstein explained different observations about photoelectric effect by applying Planck's quantum theory. According to this theory, each quantum of light called photon has energy equal to h nu. When photon hits the metal atom, it transfers its energy to the electron. Energy equal to threshold value is used up for bringing about the ionization, and the remaining energy is converted into the kinetic energy of the electron. The quantity h nu is called work function and is equal to the ionization energy of the metal atom. That is, ionization energy of the metal atom is equal to h nu naught. Thus, h nu, the frequency of light which we fall on the metal surface, is equal to h nu naught, that is work function, plus half mv square, that is kinetic energy. Evidently, if the frequency of incident light is equal to threshold value, electron will be emitted without any kinetic energy. Further, intensity of light means the number of photons hitting the metal surface per unit time. Thus, increase in the intensity increase the number of electrons emitted, but will have no effect on their kinetic energies. As we know, h nu is equal to h nu naught plus half mv square. So kinetic energy, that is half mv square, is equal to h nu minus h nu naught. The equation shows that kinetic energy of the electrons emitted varies linearly with the frequency of the incident radiation. Thus, when we plot a graph between kinetic energy of the electrons emitted and the frequency of incident radiation, then we will find that it will be a straight line with slope equal to Planck's constant, that is h. This gives one of the method to find the value of Planck's constant. Heat capacity of solids. Usually classical physics, it is found that the heat capacity of all monoatomic solids metals should be constant and equal to 3R. Dulong and Petit's law. However, experimentally it is found to be true only at high temperature. At low temperature, the value is found to be less than 3R and the value approaches 0 as T approaches to 0. The variation of molar heat capacity of a few elements with the temperature is shown in figure 1.7. When we draw a graph between temperature in Kelvin and Cv in R, then for different atoms, or metal like silver, copper, we get a graph like this. Einstein explained the variation of heat capacity with temperature again by using Planck's theory of quantization. Now, comparison of classical mechanics with quantum mechanics. As we discussed earlier, classical mechanics deals with macroscopic particles, quantum mechanics deals with microscopic particle. Classical mechanics is based upon Newton's law of motion, but quantum mechanics takes into account Heisenberg's uncertainty principle and de Broglie concept of dual nature of matter, that is particle nature and the wave nature. Classical mechanics based on Maxwell electromagnetic wave theory, according to which any amount of energy may be emitted or absorbed continuously, but quantum mechanics is based on Planck's quantum theory, according to which only discrete value of energy are emitted and absorbed. In classical mechanics, the state of a system is defined by specifying all the forces acting on the particle as well as their position and velocities. The future state can be predicted with certainty, but in case of quantum mechanics, it gives probability of finding the particle at various locations in space. What is the relation between quantum mechanics and classical mechanics? The relation between quantum mechanics and classical mechanics is found by observing the conditions under which quantum mechanics give the same result as classical mechanics. A few cases are given below. When the velocity of the macroscopic body is much less than the velocity of light, means v, that is much less than c, that is speed of light, quantum mechanics gives the same result as Newton classical mechanics. When the Planck's constant approaches the limit 0, the time independent Schrödinger wave equation reduces to Newton's second law. When the system is in highly excited state, both mechanics give the same result. It is called Bohr's correspondence principle or principle of complementarity. Bohr models of atom. To overcome the drawback of Rutherford's model of atom, to explain the line spectrum of hydrogen, Niels Bohr, a Danish physicist, in 1913 proposed a new model of atom based upon Planck's quantum theory. This new model is called Bohr's models of atom. The main postulate of Bohr models of atoms are as follows. An atom consists of small, heavy positive charge nucleus in the center and the electron revolve around it in circular orbit. Out of a large number of circular orbits theoretically possible around the nucleus, the electrons revolve around in those orbits which have fixed value of energy. Hence, these orbits are called energy levels or stationary states. The word stationary does not mean that the electrons are stationary, but it means that the energy of the electron revolving in a particular orbital is fixed, does not change with time. The different energy levels are numbered as 1, 2, 3, 4, etc. and designated as K, L, M, N, O, P, etc. starting from the shell closest to the nuclei. So, see figure 1.8, circular orbitals around the nucleus. The energy of different stationary state in case of hydrogen atom are given by the expression called Bohr formula. Energy in nth state is equal to nth orbital is equal to minus 2 pi square me raised to power 4 upon n square h square. Substituting the value of m, that is mass of electron, e, charge of the electron, and h, that is Planck's constant, we get energy in the nth orbital is equal to minus 13.6 upon n square electron volt per atom. 1 electron volt is equal to 1.602 into 10 raised to power minus 19 joule, where n is equal to 1, 2, 3 stand for first, second, third level respectively. Thus, the first energy level n is equal to 1, which is closest to the nucleus, has lowest energy. The energy of the levels increases as we move outward, starting from the first level. Thus, the energy of the various levels are in the order of first is less than second, then less than third. As we go away from the nucleus, then the energy will be increases. For hydrogen atom-like particle, that is helium positive, lithium 2 positive, etc., containing one electron only, the expression for energy is n is equal to minus 2 pi square mz square e square upon n square h square. By putting the value of E, M, H, we get minus 1312 Z square upon N square kilojoule mole inverse, where Z is the atomic number of the element. Third point of Bohr main postulates of Bohr model is, since the electron revolve only in those orbits which have fixed value of energy, hence electron in an atom can have only certain definite and discrete value of energy, not any value of their own. This is expressed by saying that the energy of the electron is quantized. Fourth postulate is like energy. The angular momentum of the electron in an atom can have certain definite and discrete value and not any value of its own. This only permissible value of angular momentum are given by the expression mvr is equal to nh upon 2 pi. That is, angular momentum of electron is an integral multiple of h upon 2 pi. Here, m is the mass of the electron, v is the tangential velocity of revolving electron, r is the radius of the orbital, h is the Planck's constant, n is an integer. In other words, the angular momentum of an electron can be h upon 2 pi, 2h upon 2 pi, 3h upon 2 pi, etc. This means that, like energy, the angular momentum of an electron in an atom is also quantized.